Hi, everyone. Welcome back again. This is really cool. We're actually on Ken Shoulders number 30 today. We've done 30 of these, so it's pretty neat. This one is really, really awesome. I did talk to Chris Baskar about nuclear waste remediation, and I believe that the paper that we're going to read today basically talks about it because it's talking about nuclear cluster reactions, and I think this is the mechanism for deradiating nuclear waste. And Chris said it can be done in as little as 48 hours with charge cluster technology. So, and there's other stuff that comes out of this too, but that's kind of the one of the main things. So, Brendan, you can go ahead, and then I'll read a little bit later on.
Okay, thank you very much, Eddie. Okay, so the title of this is Observations on the Role of Charge Clusters in Nuclear Cluster Reactions. Ken Shoulders and Steve Shoulders. Note, entered the 2nd on the 19th of February 2003, John Dash has requested the removal of data relating to this work on the grounds that his samples were likely contaminated during a meteorological rolling process, um, thus weakening the claims of transmutation. Although adequate warning of such an effect is included in this paper, the authors gladly comply with the request of John Dash and leave the data intact, but add this additional warning as to the interpretation of the data. John Dash is not to be held responsible for any data presented. Abstract. Deuterium-loaded palladium foils produced by both produced by both electrolytic and ultrasonic processing have been microanalyzed for nuclear reactions. The characteristic strike marks of charge clusters, known as EVs, or EVOs, exotic vacuum objects. EVs
Yeah.
is electrovalidium,
Yeah.
have been found to occur concurrently with nuclear reactions in micrometer-sized areas. In the electrolytic case, the reaction is attributed to charge clusters generated from mechanical energy, first stored and then suddenly released from a brittle metal lattice through the mechanism of fractal emission of electrons. For the acoustic case, EVs, electrovalidium, or EVOs, exotic vacuum objects, are
Yeah.
generated by charge separation in a collapsing bubble. When areas previously free of low energy nuclear reactions are bombarded with either vacuum or air by externally generated charge clusters, nuclear reactions are produced at the bombardment site. Charge clusters are considered to function as a collective accelerator capable of injecting a large group of nuclei into a target with sufficient energy density to promote the nuclear cluster reactions observed. So number one, background. Highly ionized micron-sized clusters of electrons having a soliton behavior along with number density equal to Avogadro's number have been investigated by Ken Shoulders since 1980, reference 1 and 2, for use in electronic systems. To facilitate daily discussion of the entity, a short Latin acronym has been adopted, and the structure is called an EV, for strong electron. Their organizational properties have been theoretically studied and reported by E. Pickman and R. Zorkowski. The origin of an explosive emission process capable of producing this extreme state of matter has recently been described by G. Mesias. What is seen in the laboratory is extremely energetic. What is seen in the laboratory is an extremely energetic entity capable of being transformed into a wide range of action-producing variations. Measurements have been made showing there are no included ions to a limit of at least 1 ion per million electrons. The total number of electrons in a 1 micrometer diameter EV is 10 to the 11. This number allows for inclusion of about 10 to the 5 nuclides that would escape detection by measuring the charge to mass ratio of the structure in such a primitive way as time of flight. For all practical purposes, the entire ensemble of electrons and nuclides would be collectively accelerated to the velocity of electrons. This gives the effect of a very simple and efficient nuclear particle accelerator.
Wow.
Nuclides can be added to the basic EV, electroberyllium or exotic vacuum object, to such a high level that the net charge becomes positive. Under this condition, there is no valuable collective acceleration, although other interesting effects occur. Over time, a number of observations have been made showing that the characteristically high energy density of EVs are enhanced further by interaction with certain target materials. The simplest observation method is to allow an EV to strike a metal electrode and note the magnitude of the plasma plume rising due to the explosive decomposition of the EV order. On some strikes, there is a copious X-ray production, very energetic plasma plumes, and a wildfire effect to be discussed later. Conversely, other strikes cause a normally energetic microplasma plume without the higher energy output. The cause of some of these differences, as seen on palladium foil, is the subject of this paper. In the interest of brevity, we will use the term NEV to designate EVs containing nuclides. In the scenario being developed here, the NEV acts as an ultra-massive negative ion with ion to charge to high charge to mass ratio. This provides the function of a simple nuclear accelerator. It is not the intent of the observations presented here to either add to or make or take away anything from the ongoing discussions of low-energy nuclear reactions. Rather, it is the intent to show a similarity between electrolytic, sonic, and gaseous discharge methods for producing the effects observed. However, it is difficult to explain the observations without some extraordinary means of introducing foreign material. Whoopsie, whoopsie. Wait a minute. Okay, 3, 1, 2, 2. That's it.
Yep, that's the one.
These are some interesting pictures.
Yeah.
Wow.
They're going to talk about them here in a second. Yeah.
2. Strike bark interpretation. as a reference to what a normal EV strike on a metal foil target looks like. Figure 1, that's this figure here,
Yeah.
shows an example produced on an aluminium target having a thickness of about 6 micrometers. In this case, the EVs were produced by a very simple external power source consisting of a handheld Tesla coil applied in air. The backside of a typical strike on the same material is shown in figure 2. It can be seen that the energy of the strike is sufficient to penetrate the aluminium. Using a higher resolution chromium film on glass type of witness plate, figure 3, shows more detail of the energy center for the same kind of strike without having much lateral thermal transfer through the target. Strike is about 3 micrometers in diameter. This should serve as a reference for the core size of energy that is delivered to the PD. I think that's
Palladium.
palladium.
Yeah.
Is lead. Palladium sample being investigated. When higher melting point materials are struck in vacuum by an EV, the craters change in both size and shape. Figure 4 is an example of a strike on a stainless steel metal foil, 13 micrometers thick. The backside of the foil is shown in figure 5. Well, it's not the other, it's on the other page.
Yeah.
Once again, there is adequate energy for penetration. So I'll just go to figure 5 just to show you. There's figure 5 there.
Yeah, that's wild looking.
Wow.
Right?
Okay. So once again, there is adequate energy for penetration. The particular splash pattern of ejected material on the backside is caused by using an aluminium backup plate to help suppress charge accumulation on the high resistance stainless steel foil. Without this plate, the negative charge density can be so high that the EV is unable to land and is unable to land, and it will skip away to deposit energy elsewhere. The arc literature has many examples of this type of strike mark, often called cathode craters, but there is difficulty in distinguishing between cathode and anode craters on bulk materials by appearance alone. This point is often complicated by not being able to tell which electrode is a cathode and which is an anode. Further exasperation results studying exasperation results by studying work done on unipolar arcs where a laser beam strikes. Whoopsie, sorry, I'll read that again. Further exasperation results by studying work. What's this? Is this one? Where is this going? Work? Is this? It starts here.
Yeah, further exasperation results by studying work done on unipolar arcs, where a laser beam strikes a surface having a single potential.
And produces a miniature thunderstorm of charge that first separates into positive and negative clouds and then forms an EV destined for the electrode that appears positive to this newly formed negative entity.
Isn't that wild that it goes positive and negative clouds, and then that's wild.
Yeah,
I
black
thought,
and
wow,
white. Yeah.
wow.
This is his best paper yet.
Yeah, it's a gooder. Yeah, definitely.
In fact, both cathode and anode craters do appear very much alike unless analyzed at high resolution. This analysis is not easy to do on most bulk materials, such as those used here. The craters seen to both sonically, so the craters seen on both sonically processed and electrolytically processed surfaces share the enigma of the unipolar arc. Cathode and anode marks are largely indistinguishable. Fortunately, all externally generated EVs, where the distance is large and filtering is possible, the polarity problem is largely overcome. The target is the anode. Pit 3. Palladium sample preparation. 2 samples of palladium treated by different processes were contributed from other laboratories. A sample was sent by John Dash of Portland State University. A slightly similar sample was used by Dash, reference 6, in an early cold fusion paper showing nuclear conversion in micrometer-sized areas. The particular sample we received was about 100 micrometers thick and had been electrolytically treated in heavy water using sulfuric and acid electrolyte on the 26th of July 1993. According to Dash, the sample was immediately washed in deionized water and stored in a covered plastic dish. A second sample treated by ultrasonic process was contributed by Roger Stringham of eQuest Sciences. The sample was run in D20 deuterium oxide, is that right?
I think so. I'm not sure. Yeah.
D20 on April the 29th, 1996 in reactor M11B and was originally a foil 100 micrometers thick. The received sample consisted of bits of palladium that were energetically detached by cavitation from the main palladium foil and had fallen to the bottom of the ultrasonic apparatus. The samples analyzed were about 0.5 millimeter in extent across their diameter. They were tested in the as-received condition. Number 4, tests on the Dash sample without external simulation. Initial tests on the surface morphology of the sample were done in the author's laboratory using the scanning electron microscope to see if EV, which is electroviridium or EVO, exotic vacuum object, strike marks could be located that would likely arise from fractal emission. Such strike marks were found, although they differed slightly from the standard EV marks produced using the aforementioned methods. A typical example is shown in figure 6. I'll just go to figure 6. There's figure 6 there. Figure 6. Although the small bright mark in the center is somewhat characteristic of an EV strike, the one on the extreme right is more typical. This mark is magnified in figure 7. Let's go to figure 7. Where's that? So figure 7. So that's figure 6 and 7. The size of the strikes are smaller than is usually seen by external EV generation methods, and the metal structure of the base palladium has altered their appearance slightly, sometimes producing a molten elongated cavity aligned with some metallographic feature. In all likelihood, the main strike hit large black area in figure 6 and was blown away with it. A slight light colored decoration of the lower edge of the crater shows effects of evaporated material as the ejected fragment left. Figure 6 and 7. Brittle nature of the material shown in figure 6 is apparent from the shape of the fracture lines. Also, figure 6. Also, there are melted regions testify to an intense heating process. An X-ray microanalysis of almost any area of the surface that has not been subject to a disruptive process is shown in figure 8. And is basically pure palladium. On the other hand, an X-ray microanalysis of a typical fractured region like that shown in figure 6 is shown in figure 9. It's figure 9. And depicts quantities of magnesium, calcium, silicon, galadium. Is that galadium? And gold, along with, I think that's galadium, I'm not sure. That's gold, along with the base palladium signature.
Transmutation. Amazing.
Many examples similar to the one shown appear on the substrate, although on this particular sample they are widely separated. It is possible that these new materials were produced by nuclear reactions involving the two major materials initially present, namely palladium and deuterium, although they could have conceivably migrated into the region along grain boundaries.
What? I hope he explains that one.
Taking the nuclear reaction view, it is the author's contention that the craters on the surface are caused by a locally created fractal emission site, then produces a NEV strike, and that in turn this nuclear cluster input is. Let's done that again. Is it 6 or 5? Oh, have I just gone for 5?
You're on page 4 still at the bottom. You got to read the last.
Bottom.
Yeah.
Okay, so I want page 5.
No, 4. You got to read that last part at the bottom there underneath that chart.
Okay, so
Right?
right.
Because this is what I've highlighted. I'm just going to read the section that I highlighted and then I'll let you read. Taking the nuclear reaction view, it is the author's content that the craters on the surface are caused by locally created fractal emission sites, and that's super important. And that's just like the start of this process. And then that then produces NEV strike, and that in turn, this nuclear cluster input is responsible for the nuclear cluster reaction produced. Super important, right? So yeah, just read that last little bit.
A wide variety of crater shapes would be expected on such an active surface, that some of the most energetic strike marks would be carried away with the ejection of a brittle metal material chunk would be expected as well. In fact, brittle chunk ejection is the sine qua non of the surface. In this case, most of what remains to be seen would be the ineffective strikes. The ejection of incompletely used nuclear nuclear fuel material is not a desirable trait, but is commonplace in this sample. In the next section, an example will be shown of more complete retention of material using an external initiation method. Number 5, tests on the dash sample with NEV simulation. A primitive EV generator was used to bombard a localized region of the same sample just discussed. It consists of a handheld Tesla coil of the type designed to locate vacuum leaks in glass apparatus. A region of the sample was masked off by a dielectric shield. And then, with the sample grounded, sparks were allowed to strike the surface from a distance of about 1 centimeter. Small flashes are produced whenever the spark terminates on the surface. This is the signature of an EV strike, and it dependably produces the kind of mark shown in Figure 1 and 3. Figure 3, provided there is no added energy from the surface itself. Although the strike mark produced by the above method of generating an EV is very consistent on the standard witness plates discussed, there is no assurance as to the kind of there's no assurance as to the kind of a number of nuclides loaded into the structure. When this EV loading is an important parameter of a nuclear reaction produced by an NEV, it may be as it may be when working with deuterium loaded palladium. Such a charged method of loading may be found insufficient for consistent work. Whoopsie, that's just occasionally one of the strikes on the material being analyzed produces a result that is uncommon to the low energy EV strikes shown in either Figure 1 or Figure 3. An example of this shows in Figure 10. Figure 10 there, on a region of the surface that includes a brittle fracture on a thin surface layer. This layer has been effectively peeled back by throwing molten material sideways along the path of propagation. Although the NEV strike may have initiated the process, continuation appears to be self-propagating due to locally added energy. This is the hallmark of an exothermic process. And if the active material extends to a great depth, complete runaway can occur. In the center region shown in figure 11, that's 11 there, and magnified in figure 12, the X-ray analysis shown in figure 13, I'll just go there to quickly go. Figure 13, so that's figure 13 there. The X-ray analysis shown in figure 13 defines the production of either new material or something foreign included in the substrate along the boundary defined by the dark marks. Although an inclusion of dirt is easily you're going to take over in a minute, Eddie.
Yeah,
Easily suspected for the cracks shown. No suspect material appears unless the region is involved in an energetic strike.
Awesome. Thank you, Brandon, for reading that. I'll take over. The explosion in this region was produced by bombardment with an externally produced NEV, and the strike mark can be clearly seen. In addition, there is some surface decoration.
Decoration, I think that is.
Yeah, showing that defines an energy release which has scored the surface, producing a light-colored region below the main strike. The cause of this wildfire will be discussed later. In some regions, there is an exception to the rule of ejecting a brittle piece of substrate material. Figure 14 shows a strike region where gross melting occurs in a way that is also very uncommon for EV only energy deposition on benign substrates. This melted region seems to have been moving sideways at the time it was frozen in place, keeping the nuclear fuel bound to the surface, as it is here, is more desirable than losing it through brittle fracture chunks being thrown off. Unfortunately, electrolytic processes need the brittle structures to serve as the nuclear initiator. Separation of the process of initiation and fueling would be desirable. An example of what appears as wildfire propagation of energy shows in figure 15 and 16. This effect has also been seen on other palladium surfaces. It is quite pronounced here. The runaway process was triggered by the arrival of an externally made NEV. The energy feeding the process seems to emanate from the cracks formed in the brittle top layer of palladium. This layer is about 0.1 micrometers in thickness and extends over the entire surface. It would seem incumbent on this highly stressed layer to either peel or otherwise break away from the base material in an explosive fashion, producing fractal emission of electrons. An input shock from an externally supplied EV would likely supply a trigger for this process. The X-ray microanalysis of figures 15 and 16 are shown in figure 17, and it says 9, but I think it's 19, or maybe it is 9, respectively. The analysis of figure 16 was done well centered on the large dark crack on the left. Analysis from figure 15 was done on the crack on the right side. When the bright melted area slightly above center and left in figure 15 was not analyzed, there was nothing but palladium showing. Apparently, this area was below a critical threshold of energy density or size for nuclear cluster. Um, for nuclear cluster. Figure 18.
Reaction. There's a word at the bottom that says
Oh,
reaction.
reaction. There it is. Yeah, I knew there was something missing. I couldn't see it. Um, Figure 18 shows an area having a mixture of cracks, molten spheres of material, and an EV strike that has been partially obliterated by other activity. There is a minimum amount of wildfire activity in this eruption. Figure 19 is an X-ray analysis of the dark crater on the left side of figure 18. Small amounts of foreign material shown here. With the limited analysis done, the surface of this material is unknown. Mechanical storage of energy is thought to be the source for the small EVs produced. It has been determined both experimentally by the author and theoretically by G. Messiates that the size of the EV structure is a function of the high specific energy delivered to the metal. Higher energy density produces smaller structures. The locally obtained energy from micro-sized sources gives a higher input.
Micrometer size sources.
Micrometer size sources gives a higher input energy density than the best external powered sources using an EV generator, usually limited to the 1 micrometer size range. The wildfire process appears to have little value in the mode seen here because it is below the threshold for triggering the main nuclear cluster reaction we seek. And I think that's really important that there's a limit, like a lower limit there. So far, there have been no nuclear transitions observed that are associated with wildfire action. Its principal function has been more accurately pointed to mechanical fractal emission, and again, that's really important, the fractal emission part, as the local source of stored energy to trigger a nuclear cluster reaction through the instrument of NEVs. So this is number 6.
Number 8, page 8, number 6.
Yeah, it's number 6. Tests on the eQuest samples. Ultrasonic processing methods produce a different surface morphology from samples produced electrochemically. The ultrasonic method tends to wipe out its past surface history more rapidly than does the electrochemical method. It does this by both adding colloidal
Colloidal.
colloidal particles of the parent metal to the surface, and at the same time removing material by mechanical shock. EV craters that would normally look very sharp on the unmolested surfaces show a fuzziness characteristic of repeated pluming.
Pummeling. Pummeling.
Oh, pummeling, yeah, so they're being hit. Nevertheless, figure 20 is a view that shows 4 classic EV witness marks similar to those shown in figure 4 and characteristic of most bulk material surfaces having a high melting point. Figure 21 shows a crater produced in a protected region. Brittle fracture is evident here. There is evidence of melting shown deep down in the crater, signifying an energy production process at work that is not strictly surface related. In a private discussion, Roger Stringham has stated that the edges of such craters are usually the location of transmuted materials, and that's really important. I think that statement right there. This is in accordance with what is found in electrolytically treated samples.
Electrolytically, that's right.
yeah, treated samples, where it is easier to view the undisturbed residue of a reaction. The origin of the observed strikes has not yet been clearly delineated in any theory known to the authors. However, work has been done on EVs produced underwater by electric methods, and the results give the same witness marks as those shown earlier from the gaseous production methods. The fact that light slows, the fact that light shows as 50 picosecond flashes in the sonoluminescence process associated with cavitation, and this corresponds to the time known to occur in EV formation processes, points to the possibility of sonically produced EV structures made through cavitation charge separation. I think that's an important statement too. Figure 22 shows a scanning electron microscope photo taken of a foil prepared by R. Stringham and photographed by J. Dash and R. George. The micron mark in the photo has been restored by the authors and is only approximate. The most obvious thing that can be seen at this low magnification is the large impact craters created by a few strikes from some unknown energy concentration processes, probably having to do with the momentum transferred from the fluid bath to the surface. These strikes both totally penetrate the foil and also knock out trumpet-shaped brittle fragments on the reverse side of the strike. These strikes are more like driving a nail through the material, and according to the notion being presented here, would not likely yield nuclear reactions. In nuclear cluster reaction theory, the energy density is the all-important parameter to maintain. Large, low energy density strikes represent a loss of energy gain in the process of nuclear conversion. The measure of energy density might be found most expeditiously.
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 Thank you, Chip. um, uh, Expeditiously by the number and type of nuclear transitions produced. The main point to be made here is that marks are made on the ultrasonically produced surfaces that are very similar in size and shape to those made by EVs under more controlled conditions. Examples of sonically bombarded surfaces taken from the literature show many classic EV strike like witness marks. Number 7, discussions of observation. The nuclear reactions produced in the observations made have many things in common, but the most outstanding of these is the clustering effect. All reactions found occur in a region of only a few square micrometers in extent. This is also the size realm of the NEVs used to either fuel or trigger the events. From this observation, it is necessary to conclude that some nuclear reactions are fundamentally an intense event involving large numbers and not one of widely associated events, isolated events working individually at an atomic level. For only a small set of observations, it is increasingly apparent that there is a threshold effect in which no new or foreign material is produced until the physical size of the stressed area is above 1.5 micrometers in lateral extent. Additionally, the percentage of new material seems to increase as the size of the reaction grows. The production of high atomic number elements also increases with reaction size. Before the observation made in the course of this work can be taken seriously, many more samples must be tested. In search for the validity of this threshold effect, one must consider that the energy density of the initiator sets the threshold size of the nuclear cluster reaction. High energy density in the initiator would produce small clusters, just as it does with high energy individual nuclide found in standard nuclear processes. The low energy density of our initiator process would be expected to give rise to larger clusters containing more events with
concomitant
low energy byproducts. NEV generation is a compression process that blends smoothly with other compression processes like cavitation excitation.
Yeah.
But the maximum density is limited by unknown factors. Again, that compression part is super important. For other work done in the area of high charge density effects, the timing of the events being studied here occur in scarcely more than a few tens of picoseconds, so super fast. Even with this short interval of time, there is a series of steps leading to the final result we see in frozen images. For the self-triggered electrolytic process, first there is a slow loading process that produces a brittle product. Next, there is a very rapid brittle fracture of sufficient magnitude and shape to give rise to an NEV that is loaded with whatever nucleons are available. In the case considered here, it is likely that over 100,000 deuterons are included. These nuclei are then hurled with the high density afforded by the EV compression process into the parent material. Again, super important. This is done by a collective acceleration at a low applied voltage in the kilovolt range. Usually it's about negative 2,000 volts. But having the equivalent velocity of megavolts due to the acceleration mechanism. The theoretical basis for a controlled microvolume D to T thermal nuclear process is described in the paper by V. Yeah, Russian guy, obviously, and Vogel. In the model, the authors interact a local laser-produced intense microbeam of heavy ions with condensed matter. The extreme state of matter produced in the gigabar pressure range is generated by interacting shock waves like those demonstrated in the EV technology. Functionally, the two processes are nearly identical, with the NEV process being the easier of the two. At this point in the reaction process, there is a void of knowledge, but we will attempt an ad hoc explanation of the observed results. The most outstanding observation of cold fusion in general is that the byproducts of the nuclear reactions produced have much lower energy than conventional hot fusion reactions. In our opinion, this is largely due to a nuclear cluster reaction having an unknown form of coherence. That is like the ultimate statement, because it's that coherence that matters so much.
Yeah.
Definitely, right? Is its phase conjugation. It's kind of back to that sort of scenario.
Yep. Talking about scalar energy.
Yeah, exactly. As in many harmoniously coupled reactions, it is easier to dispose of excessively high peak energy by coupling them into an interlocked network of lower energy coupled states. A supreme example of this is found in the Mossberg
Mossberg.
effect, whereby a solid lattice of atoms acting in unison taking up takes up departing gamma photo recoil energy. I found this is really interesting. In a like fashion, the most energetic components of our nuclear cluster reactions are transferred to multiple lower energy states through group actions. This can be a conversion process without loss. That's really wow. Carried to an extreme, a theoretical conversion could be made in which all of the energy in one class of nuclide is converted to another without any external indications. This is wild. This super transmutation would be the equivalent of superconductivity and really not that much more surprising. That is a wild statement right there. We need to go back and look at that at some point. In the imperfect world in which our process is embedded, the debris of nuclear reactions is transmuted into heat and
transformed
into heat and some errant energetic particles. It is the effect of nuclear cluster reactions with their propensity for low levels of peak energy output that produce the most desirable properties, and not whether the process is either cold, tepid, hot, low energy, or high energy. The underlying merit of this unspecified process stems from the
salient
fact that some still unknown coherent, there's the word again, group action lies at the root of all this. So that, again, it's so important. Electrolytic and sonic processes occurring in solutions are difficult processes for extraction of certain operating mechanisms. By bombarding surfaces in vacuum with externally generated NEVs, the brittle fracture requirements become null, and nuclear fueling processes can be separately investigated in great detail. What is immediately apparent here is that any area on the surface becomes a willing site for nuclear reactions and is
concomitant,
yes.
Isotropic conversion. Wow, I'll have to go back to that too. However, there remains a requirement for cluster action in which billions of atoms cooperate to produce a more desirable endpoint. And that's a really important thing. There's billions of these things all doing the same thing, right? That coherence. With this crude method of generating an NEV used here, there can be no accurate determination of either the energy level or the number of nuclides included in the NEV. The critical size must lie between the limits of the successful 3 micrometers, and 3 micrometers is 3,000ths of an inch, you guys, if you don't know. 3 micrometer clusters used by the authors, and the largest of the ineffective strike seen around 0.5 micrometers in diameter. There is also a contribution of energy from the substrate that cannot be accurately accounted for at this time. Taking advantage of the mechanically stored energy is most likely a matter of supplying a mechanism for concentrating the available energy of many small strikes that lie below the triggering threshold. Arranging for a particular fracture geometry would be one such method, but this technique is felt to be impractical because external NEVs generation is much easier. 7. Conclusions. It has been determined that electrolysis of palladium in heavy water produces a brittle layer on the surface that fractures in a manner producing fractoemission of electrons. Again, that's so important, fractoemission of electrons. These electrons are organized in concentrated electron structures containing nuclide called NEVs, and then collectively accelerated into the surface where they produce a nuclear cluster reaction. Sonically treated palladium surfaces in heavy water are also subject to the same dense electron and ion cluster treatment that arises from the charge separation in a collapsing bubble. A nuclear cluster reaction is also produced from this process. Deuterium-loaded palladium foils spark bombarded in air with an electron cluster incidentally loaded with nucleons produce nuclear cluster reactions. Indications are that the cluster type of nuclear reaction is responsible for the limited number and mild nuclear reaction products escaping the reaction site that produce them. In the limited work done here, there is the appearance of a threshold for the nuclear cluster reactions observed. The threshold is connected to a physical size for the eruption seen and is near 3 cubic micrometers of material. In addition, there seems to be a preferred production of heavy nuclides with increasing size of the disrupted area, which is the end of the paper. And then on the last page, there's some awesome references. And the one that I sort of went to was the Messiates one. And it's one that I haven't actually looked at yet. Some of the other Ken Shoulders, Evie, A Tale of Discovery, the first one, that's the book that we're actually going to be going through at some point here that he wrote. So this is an excellent one, like Chip said. Do you guys have any comments or?
Yeah, I guess I'm most interested in this wildfire process, this COP over 1. Is that what he is talking about? We have kinetic energy. We're imparting with very low mass, but mass times velocity is momentum, very high velocity. And he's trying to differentiate this kinetic effect, blasting holes in the foil, from the nuclear effects that are occurring, and then the auxiliary nuclear effects that are occurring over a period of time and demonstrated by within the crater themselves. And there are a couple of those photomicrographs around figure 8, figure 10 in that general area of the paper show that. So this is a very difficult experiment to try to quantify, but what he is saying is this kinetic effect combined with obviously the nuclear effect, the nuclear reaction, that transmutation effect, the super transmutation effect, which I find really interesting.
Yeah.
All this combines to produce something that he cannot quantify. And that cannot quantify, like you already said, Ed, is very likely 0-point energy. He's pulling, that's the freaking clutch.
Yeah.
He's pulling, he is seeing and demonstrating he cannot quantify it. All he's doing is pointing out there is this super transmutation effect that is occurring. And I see that as the secret to this clutch mechanism he talks about all the time. He just engaged the goddamn scalar field, and that is coming into play here and is probably responsible for so many quantum vacuum processes that we just now are beginning to realize occur at this nuclide level.
Yeah.
With these clusters.
Yeah.
Amazing paper.
Yeah, this super transmutation would be the equivalent of superconductivity and really not that much more surprising. That's wild.
So superconductivity can be like an Einstein-Bose condensate where the entire mass of material kind of acts as one big fucking electron or proton or neutron. That's the whole idea. And so embedded in that process, we have the release of this mystery radiation that killed him, and also strongly points to this unique transmutation nuclear reaction process that is obviously dangerous with this mystery energy. But it's at the secret of everything associated with clutching the vacuum field and
Yeah.
getting 1 + 1 to equal 3, as in super transmutation.
Yeah. Yeah. And it's basically, he's trying to describe how they do nuclear waste remediation, um, with this paper kind of. And I know that Chris Beskar told me that, in as little as 48 hours, they can de-irradiate nuclear waste using charge clusters and these processes essentially, right? But he's basically saying that, one thing sets up another thing, and then that sets up this process essentially, right? And
Yes.
I think maybe the most important part here is that it's um, we will use this term NEV to designate the EVs containing nuclides. In this scenario being developed here, the NEV acts as an ultramassive negative ion with high charge to mass ratio. This provides the function of a simple nuclear accelerator. So essentially, they're creating this nuclear accelerator process that triggers, um, these other things essentially, right?
The wildfire effect.
Yeah,
It,
I think when he
yeah,
talks about the wildfire though, Chip, that he says that it doesn't really do anything in this process. Um, he's referring to it, but he's not really, saying too much about it.
he can't define it, and he's completely honest about that. He states that we see something here, we can't quantify it,
Yeah.
um, etc. But we see the wildfire for me concept is a generic uh, continuous reaction.
Oh,
In
okay.
other words, that's what a wildfire does. It gets started on its own, and it goes like hell, burns
Yep.
out in space and time. And that is created, I believe, by the addition of 0 point energy, scalar energy that is being clutched by the whole process.
Yeah. And I'm going to read another line here that really struck me. Further asper exploration results by studying work done on unipolar arcs, where a laser beam strikes a surface having a single potential and produces a miniature thunderstorm of charge that first separates into positive and negative clouds and then forms an EV destined for the electrode that appears positive to the newly formed negative entity. That's wild, right? Um,
I made a note in my book about that very same comment.
Yeah, that's on page 2,
Yeah,
bottom of page 2.
I don't
Yeah.
understand the cathode anode polarity concept. And in
Well,
you would expect that the reaction would be different if it was cathodic versus an anode reaction, whether it was positive or negative.
I
He doesn't say that that occurs
I think
because
yeah, I think he
it's hard to
says,
differentiate the anode from the cathode reactions. He just says it
yeah,
looks like that is occurring,
yeah,
but
that's
that's the whipsaw that's so critical to creating a super transmutation, it's transmutation, highly polarized, highly potentiated field right at the point of that reaction. You are literally torquing the shit out of the vacuum with a combined cathode anode reaction of some kind. He's
yeah,
dancing around the issue and he's trying to convince himself, but he doesn't have the experimental evidence. I can see what he was thinking here. We know what? We need to read this paper again next week. This is
yeah,
really, really interesting.
yeah. I sort of saved some of the better ones for later. The other thing I saw today, you guys, and some people have requested seeing this, is I've got all the pictures of Ken Shoulder's laboratories and all his equipment and all that stuff. And I was looking at them today. I'm gonna have to take a lot of screenshots. There's probably like 40 pages or something there, but we should go through them and show you guys because it's very inspiring
Yes.
to
Yeah.
see as well, too,
I
right?
had noted some other, jotted down a couple other notes here. You know, the unknown energy concentration process, the threshold effect, the compression process, obviously the super transmutation.
Yep.
Um, all of this wrapped up into this wildfire thing, which uh, gives it a time function, a reactive time function, and you have quantum chemical reactions, nuclear reactions taking place with a poorly defined electric field, both cathode and anode, black and white, like he says in there, black and white EVs, maybe. And how does that interface with the kinetic energy coming from the initial pulse or from a femtosecond laser? I mean, you could do the same thing.
Yeah.
God Almighty, this paper is amazing. What they're generating here is a goddamn photon torpedo, for Christ's sake. That's exactly how they work.
The fact that light shows as 50 picosecond flashes in sonoluminescent processes associated with cavitation. I remember when this all came out, my dad's girlfriend, her name was Peggy, and she was a master librarian at the Agricultural Research Station for the National Research Council of Canada, and had over 100 PhD scientists, plant scientists, working with her and whatnot. But she came home with photocopies of all of the sonoluminescent stuff because she knew that I was a sound guy, essentially, right? And I was thinking when I read through this paper the other day when I was highlighting it, I wish I would have kept that, or because I don't think I've got those original ones that she gave me. But she was always bringing stuff like that home, right? And the other cool part is her best friend. She also worked for the National Research Council of Canada, and she was the administrator of the radio observatory called White Lake that we have in Canada. So I had free reign of that place for about 10 years and just used to go out there and check all kinds of cool stuff out, talk to the scientists and whatnot, right? Got myself in trouble at a black hole conference once, big time, but that's a whole other story.
Oh, because you mentioned something that was probably the truth, right? So,
well, anyway. the guy was talking about saying that nothing comes out of a black hole, and at that time it was Stephen Hawking's time. Hawking wasn't there, but everyone else was. Like, it was a major thing, and I piped up and I said, Hawking radiation, comes out. But that's actually wrong too, because now we know from subquantum kinetics that it's not a black hole at our galactic core, it's a mother star. And the Hawking radiation is actually the super wave that comes out from Paul Laviolette's work. So interesting. But when I spoke up, the guy felt that I shouldn't have, and he ended the conference then and there, and everyone was just pissed. Yeah, I was in big trouble with her. She walked over to me and said, "Why did you say that?" And I said, "Because it's not true." So
yes,
there you go. Right? And here we are now.
So on your comments of sono aspects, how often, here we go again, ignoring the acoustic phenomena.
Yeah.
Once again. And that is probably also coupled to fractal emissions, because you create a nice soliton, a nonlinear acoustic pulse, and you do some crazy shit to a beryllium ferrite matrix, for instance, ceramic matrix, where you create fractal emissions sonically.
Yep.
You don't have to have electromagnetic fields involved. You can do it acoustically.
Yeah, definitely. Like this paper basically says you can do it both ways, right?
Yes. One of the secrets for our species to understand, I think, in the coming decades, is how best to combine the acoustic and the electromagnetic effects. I think there's secret barbecue sauce in that mix somewhere.
Yeah.
And we're just going to have to push the envelope a little bit and try. Is there anybody that has taken Ken Shoulder's work, number one, tried to replicate it in a high-end lab, or done anything to further what he's even discussing in this paper?
Yes.
I know Greenier talks about it, but he doesn't really have a lab, does he?
Well, he's got access to all kinds of things, but Bob does. But I would say there's someone else that we had in our group recently that would definitely have exactly what you just asked about.
Asbestos.
Yes, absolutely. And remember, you guys, that Ken
behind locked doors.
Yeah, exactly. Ken Shoulders and Chris Beskar had a business relationship, And when the Pius patents first came out, I was kind of an expert on them, and I was asked on the Jeff Rense radio show, the same radio show that William Tompkins was on many times. And I talked about a lot of this stuff on there essentially, right? I talked about Stavati and I talked about subquantum kinetics and all of these processes. But yeah, they had a business relationship. And what I was going to say was, the technology coming out of Stavati is not the Pius patents. The technology coming out of Stavati is the Ken Shoulders work.
Absolutely, because the Pius patents don't discuss the barbecue sauce.
It's charge clusters.
They don't get down to that level. And this is what I
Yeah.
like so much about this work that you're presenting. For me, it gives right, once the rubber hits the road.
Yeah. It's the like you said it, and this is right from Ken Shoulders' words. It's the clutch that engages the ether.
You know it.
Charge clusters.
Yeah,
and,
it's just beautiful.
Yeah, yeah. So yeah,
And
it's amazing.
Just describe when you're talking about the clutch that engages the ether, Eddie. A clutch is in a car. Just describe a little bit what a clutch in a car does.
Yeah. So when you're driving, like most people don't know what a clutch is now because a lot of people drive automatics. But when you disengage the clutch or let the clutch out, it allows the power to be transferred. So essentially, if you want to tap the ether for energy,
the gear sticks on the clutch.
Well, no, the clutch actually is
biplates.
Yeah, it disengages and engages the power. So when you go to shift, you push in the clutch, and then you shift the gear, and then you let the clutch out. And now you're into another gear. But when you take off, you're in first gear. You let out the clutch slowly, and the vehicle starts to move. So it's it's an indication of power transfer. Mm-hmm. How do you transfer the power? And Ken Shoulders says it's the clutch that engages the ether. These are charge clusters, but if I would go one step further,
accessing the 0 point, sort of like a clutch.
Yeah. Oh, yeah.
Accesses the 0 point. So
yeah,
that's the secret.
Yeah, exactly. And if I were to go one step further, and I did say this on camera with Chris once, and I was a little bit incorrect when I said that an etheron, a charge cluster, and ball lightning are all one and the same. Technically, I should have said an etheron, an electron, and ball lightning are all one and the same, because a charge cluster is a bunch of electrons that are spun up, essentially, right? But the more technical proper term would be something that clutches the ether is actually the etherons are actually doing the work. Yeah. If you want to get more correct about it, according to subquantum kinetics. So that's something that we need to look at. And Brandon has done simulations of the Turing wave, and the Turing wave is indeed acoustic. It is a soliton.
I heard you say that a couple of weeks ago, and I wanted to ask some more about it. Yeah,
absolutely, it is. The Turing wave is this.
That's the goddamn symphony of the universe, right?
This geometry right here, a dodecahedron. It's got 12 sides, but a pentagon on each side. And this literally, it's an implosion and an explosion. So on implosion, you're going into time-space. On explosion, it's space-time. And that's how the Turing wave pulses between the two. And every single time the Turing wave pulses, and this is the wild part, every single thing in the universe pulses at the same rate. This Turing wave
being like the soliton of ether.
It is a soliton, yeah. It is a soliton, and the etherons are. And the interesting part of this is it takes, he's talking about 10 to the 11th. That's 100 billion electrons, and it turns out from Paul's work that it takes about that same amount, 100 billion electrons, to form the Turing wave. And these little etherons are coming from space or time-space into space-time, appearing and then disappearing again. So it's a reaction diffusion, and this occurs back and forth. But every single thing in the universe pulses at this rate. If you change the rate of the Turing wave pulsing, now you're doing teleportation, maybe even interdimensional things. So this is how we control things, and it's the spin, but it's actually the precession of the spin, that wobble,
The
that
wobble.
if you can phase lock or make that wobble coherent, like you do in an MRI machine, which I've been in MRI machines like probably almost 10 times now. And every time I sit in them, I think about how they work. And so it's the same thing as an MRI machine. You make coherence, and coherence was talked about in this paper a lot, right? So
Yeah.
again, fantastic stuff. And thank you again, Chris Beskar, for handing us the golden key, because this is one of the papers that was in that group of stuff that he sent. I was on camera one day with him with Legia on potentials, and we asked for some of the Ken Shoulders patents, and Chris said that he would send them, and indeed he sent them because they're in there. There's 3 of them in there, but all of this other stuff is in there as well too, and that's all the stuff we're going through now, right? And
Yeah,
it was
in the
amazing.
previous dozen or 15 papers we've done, Ken has alluded to some of this unique super transmutation. But this is the first paper where we're really starting to point a finger at this. And completely honestly, completely transparent, I don't know exactly what the fuck's going on here, but we have kinetic effects, we have transmutation occurring,
Yeah.
we have secondary effects, wildfire effects once we create this thing. All this has happened in nanoseconds.
And what's interesting is it was saying in the paper that the transmutation usually occurs along the edges of it, and we
Deeper
do.
in the hole.
I think that we do know a little bit more. I don't know. I think this paper was written in 2000 or something, right? And in 2001, I believe, is when the very first show that we did that was called Ken Shoulders. We did it on the Proton 21 laboratory that was in Russia, and showed transmutation. And then the paper that we went through, Ken Shoulders #1, and I think there's another one that we did too, literally show transmutation with the analysis done and everything. But it all comes from the Russians, and the Proton 21 laboratory was in Russia. But the interesting thing is it was packed up and it was moved to the States, right? I don't know at what point, but that's what happened to it. And yeah, so if anybody's really interested in transmutation, I'd recommend going back to, I think it's Ken Shoulders #1, the first one that we did, that shows that there's physical pictures from the Proton 21 laboratory, analysis from it, and everything, right? So
Yeah.
yeah.
I forget which picture it is, figure 10 or 12 or whatever. He shows the transmutation is the white rimming effect deeper in the hole. So the implication is there's a time texture to it. The kinetic energy hits the surface of the palladium foil, and it takes a little bit of time to initiate the process. So you see the transmutation occurring deeper in the hole. It doesn't occur around the surface edges. It's deeper in the hole. It's very important because when you create a temporal texture like that, you create a resonance in the time field. If time is now resonant, spatial things can happen.
Yeah.
So to tie all this theoretical physics that we're beginning to understand a lot more clearly, and his whole freaking process is now making sense in we're being able to connect the dots with all this other stuff that we've never done experiments with. That's why his experiments are so extraordinary. Even looking at a tiny little fucking pockmark and breaking it out in layers is incredibly important.
Yeah. And you're right about that, because the Proton 21 laboratory, what it was is it was a 99.999% copper slug that they shot an EVO through. And indeed, it was on the backside of it where the transmutation analysis was done. And they found like a whole pile of elements back there, essentially, right? That absolutely proves it, right?
I thought it might be an idea, if you like, to just read. Remember I asked ChatGPT about what is an EVO and why are they important? I could just read out. I could read out the summary again, if you like.
Yeah,
that's quite that sort of summary, because that kind of summarizes it. So I'll just read out this. So what is an EVO and why are they important? EVO stands for Exotic Vacuum Object, coined by Ken Shoulders, a pioneering researcher in the field of high-energy electron clusters and vacuum physics.
Yep.
Shoulders discovered that under specific conditions, electrons can form dense, self-organized plasmoid-like structures that exhibit unusual properties, such
Yep.
as high energy density. EVOs can store and release large amounts of energy. Coherent behavior. Unlike conventional plasma, EVOs seem to maintain a structured self-stable form.
Yep.
Reduced inertial mass. Some researchers suggest that EVOs might exhibit anomalous inertia effects, potentially linking them with exotic propulsion concepts.
Definitely.
Potential for overunity. Certain experiments suggest that EVOs might extract energy from the vacuum or interact with zero-point energy in ways not fully understood.
Yeah, bingo.
Why
Bingo, right?
Why are EVOs important? Shoulders' work suggests that EVOs may be the key to new energy technologies. If EVOs can be harnessed efficiently, they might provide an alternative energy source. Advanced propulsion. Their anomalous inertial effects could lead to breakthrough space propulsion technologies.
Yep.
Understanding the vacuum. EVOs challenge mainstream quantum electrodynamics and could provide experimental evidence for alternative theories of the vacuum, possibly linking to subquantum kinetics.
Yes.
Biological and consciousness studies. Some theorists speculate that EVO-like structures may play a role in biological energy transport and even consciousness-related phenomena.
Biophotonics. Yeah.
So that's definitely the case. I have a slide that I don't think I've ever shown you guys. That's from David Wilcock and Stavati and Chris. That says every time we have a thought, an EVO is formed. And here's the thing. We've been talking about EVOs in the terms of energy density and packing energy in, because that's kind of what Ken was doing. But here's the other part. Not just energy can be packed in there, information can be packed in there. So that's what this thought is it's an information package, a charge cluster, an information package that goes into vertical time. And then as it comes into...
You just froze a moment, Eddie.
Yeah, he froze.
Essentially. Right?
Yeah,
that's how it works.
You're back now, Eddie. You just froze for a bit.
Okay.
So EVOs happening, can you EVO happening within the neural networks of the brain?
Pineal, your pineal is producing them.
Well, they're every. I mean, the phenomenon is everywhere.
Well, yeah, but a specific thought is an EVO or a spun up package of information. Let's not say energy, right?
Mm-hmm.
And it. I don't know if you guys heard me, but it basically goes out. It's created by our pineal gland, goes out
vertically,
and goes into vertical time,
right?
And then as it comes to fruition, it ends up in horizontal time, which ends up in our reality essentially. And there's a lot of great stuff on all of this on the Wingmakers. I did 6 shows with Legia on potentials, and if you guys want to learn about vertical time and horizontal time, there's probably no better way than to learn from there essentially, right? It's really great stuff.
Yeah.
So we'll should stop the recording because it's going to be really long.
Okay.
Guys, but if this is awesome, thank you everyone for everything and contributing and stuff.
Okay,
Amazing
thanks everyone.
stuff.
Have a wonderful rest of the week. Cheers. Take care. Bye.
Yep.